Okay, but we're recording now. Then I will upload this in yesterday's lecture. I forgot to do that. I can actually do it now if there's any dead time. But what questions do we have? Can we all see the whiteboard? Okay, good. I don't have anything prepared. I'm just here to help answer questions and boost confidence.
Is there any good resources for like common chemical processes that we could like look at and work through?
I mean, there are, but there's sort of more advanced senior level textbooks. There's two pieces of advice. Let me just grab something here off my shelf. So if you search online, Learn Chemie on YouTube has this class as a series of YouTube videos as well. Depending on which textbook you bought, there is a student workbook that accompanies the Felder version from the 2005 third edition. And it basically has questions that it helps walk you through, and it does it step by step by step. So that's another resource. But my advice is understand the homework, be proficient at the homework and the practice exam, and any example problems that we've gone through in class. Those are the best resources, I think.
Thank you.
No problem.
Wait, is it possible to go over like a problem about purge system?
Can you say that one more time, Henry?
Can we go over like a recycle purge system question?
So I heard it. Can you go over a blank system? The audio is a little rough.
Yeah.
I
I'm
think
in
you
the
could
ICT.
recycle purge.
Yeah, that's what I said.
Oh, like, okay, so like a reactor separator?
Yes.
Okay. What about it specifically? So it'll be difficult for me to come up with one off the top of my head that has numbers and everything, but I think I have a reactor separator here somewhere, or I could go to the homework. No, that's not right. Do you have specific questions, or you just want to walk through it? Like do you want to have an example you're asking, or do you have some general questions?
Yes, an example, please. It's because I got lost in the homework in one of the questions.
Okay, I think we had one on homework 3, right? With an ethylene epoxide one.
Yes. Yeah, I think homework 3 or homework 2, maybe.
I'm pulling one. Let me see if I can pull it up. Okay. I'm just trying to look at it here. Oh yeah. Yeah, 3, number 7. Okay, ethylene epoxide is produced in a reactor separator with 10% oxygen. Single pass is 15% conversion. 100% of the ethylene and oxygen recovered on the top and the epoxy at the bottom. Bottom stream has a flow rate equal to 40% the feed. The bottom stream ethylene epoxide flow rate is equal to 40% of the feed rate of ethylene. Oh, okay, so I'm just being annoying by not telling you the basis. Okay, what fraction of the separator top stream is purged? What is the recycle ratio? Okay, I think I can solve this one for us. Okay, so we've got straw reactor separator, we got our mixer, we got our reactor, we got our separator, we got our bottoms, splitter, top stream, and here. So this particular problem, let's do some shuffling of my screen, get everything together. So ethylene epoxide, oh geez, I have to look up. So I think this one's, so ethylene is C2H4. So ethylene epoxide plus 1/2 O2 is C2H4O. I believe that's correct. So if I do 100 ethylene to the system, I'm feeding in 10% excess oxygen. So that would be 55 O2. Single pass is 15% conversion. Right, so I'm just kind of walking through how I would set this one up. And 100% of the ethylene and oxygen recovered in the top stream. So this is going to be NeNO2 and then NeO. And the bottom stream of ethylene epoxide is 40% of the feed rate of ethylene. Okay. So this is equal to 0.4 times by 100 ethylene. Okay. Does that make sense so far? How many folks we got on? 10, okay. So I'm not looking at the solution, so hopefully I'm not botching this horrifically according to my solutions. So what do we say is the first starting point then, right? So what we did is we converted the description of the process. We filled in the simple information that we could from the start. Actually, let me just check my solutions. Maybe make sure I'm setting this up right. Oh, I'm so good. Got it. Okay. So what's our first starting point?
Maybe an overall atom balance.
Overall atom balance would work out just fine. So let's do an atom balance. Which one we want to start with? O or carbon or hydrogen? And in fact, carbon and hydrogen are dependent on one another. So the hydrogen balance is just twice times the carbon balance. So we actually only have two independent balances that we can do. We can do one carbon balance and one oxygen balance. Which one should we start with, you think?
I'd say oxygen.
Yes. All right, I'll see you guys in class.
Yeah, actually, I don't think it matters. I think we can do either one because we have the ethylene oxide output. So there's only one unknown for each of these, which is the unreacted one right here. So let's do oxygen balance. All right, so we got 55 coming in. And mute that one there. 55 coming in. For every 1 O2, we get 2 O's. And this is equal to our unknown NO2. For every 1 O2, we get 2 O's minus, plus, so this is equal to 40 ethylene oxide plus 40 ethylene oxide. For every 1 ethylene oxide, we have 1 oxygen. So this should result in, let's see, 110 minus 40, 70, 35. Right? All right. 35O2. Check my solutions. Oh, I don't know if did I calculate that here? My solutions? Yeah, 35 oxygen. Okay. I'm not making any mistakes doing it in my head. And let's do a carbon balance. We could also do extended reaction, but we did an example of extended reaction yesterday. So I guess it's good to go over the carbon atom balance. 100 ethylene, 1 ethylene is equal to 1 carbon. Leaving the system, we have 40 ethylene oxides at 1 EO is 1 carbon plus our unknown ethylenes, 1 ethylene is 1 carbon, and then this should be just 16. Oops. Okay. What's next? The question is asking, what fraction of the separator top stream is purged? Okay. So that's not trivial because we actually have to work out basically how much is being fed to the system in order to figure out how much is being purged in the system, right? We know that 100% of the ethylene oxide is coming out through here. So if we can work out how much ethylene oxide we're making, then we can kind of work out how much is being purged to the top of the system. Okay, let's see. Okay, yep. So if we work out that we have 15% conversion, 0.15 is equal to moles reacted over moles fed. This will tell us that we have reacted 40 moles of the ethylene oxide. So we formed 40 moles of ethylene oxide. And then this will tell us how much ethylene is being fed to the reactor, which we'll call that stream 2. 1, 2, 3, 4, 5, 6, 7. All right, so this is actually quite similar to the example we did in class. And I have in my solutions here that the moles of 266.7. So that means if we do an ethylene balance on the mixer, then that tells us we have 100 moles being fed plus our unknown amount of ethylene in stream 7, which is the recycle, is equal to 266.7. So then we know that the N ethylene in stream 7 is equal to 166.7 moles of ethylene. Okay, are there any questions so far? So I'm gonna keep on going for just one more step maybe, and then we're not gonna answer the whole question, but we're kind of just going in a loop of what we can resolve. So if we go back, so now we know that this is 266 ethylene, and this is 166 ethylene. And so now we can actually figure out how much we're purging from the process, and we can figure out the recycle ratio also. So the splitter here is what I would call a dumb unit operation, meaning that it doesn't do any separations. The constant compositions are the same. And so these are some of the basic processes that you kind of have to know. So a mixer, just mix two things together. Splitter, separate it into two different streams with the same composition. So we know the ratio or the mole fraction here of the ethylene to oxygen. So that means we can work out what the total flow rate is on stream 7. So we know that the ratio is for every 60 ethylene, we have 35 O2. So we have 60 ethylene for 35 O2. So that means we know that the flow rate of oxygen in stream 7 is equal to 166.7 ethylene. For every 60 ethylene, we have 35 O2. And that is going to be equal to, oh geez, I got to just knock this one out here. I can't do this on my head. 166 divided by 60 times 35, 96.8. 96.8 O2. And so then the total flow rate of stream 7 is 166 plus, let's just say 96.8, 262.8, 262.8. Okay, so now we can figure out how much is being split. So if we did a total balance on the splitter, we have N5 is equal to N6 plus N7, right? N6 is the 60 plus 35, so that's 95. N7 is 262.8. Geez, so much math. Plus 262.8 is 357.8. 357.8. And I think I have, wait, I have an error somewhere. I'm looking at my solutions real quick. 266.7, 166.7. Okay, okay. In my solutions, I did it for just the ethylene to figure this fraction purged out. So that's a little bit different. Okay, so then the fraction purged is going to be N7 over N5, right? N5 is the total amount sent to the splitter. N7 is how much is being purged. So that's 95 divided by 357.8. And 95 divided by 357.8, 26.266. And that is what I got in the solutions. So I did not totally botch that. Okay, so then the rest of the questions I think fall into place pretty easily from that point onwards. So on number 7 of homework 3, what is the recycle ratio? Well, we basically already calculated that. It's stream 7, 262 divided by the feed, which was 155. So you can calculate that pretty readily. And what is the overall ethylene conversion? Well, we actually already knew that one is 40%. That was provided in the problem statement. So yeah. How does that make everyone feel? So I would say this is, that's pretty typical. And so we worked this one out and we solved it in about 15 minutes with talking through each and every step. A problem of this difficulty for a reactor separator would be something that you should count on maybe being worth a quarter of the exam. So even talking through the problem, working it out, being fairly diligent at which steps that I'm showing, this is very easy because, you know, an hour for 15 minutes times 4, that's the length of an exam. We could finish the whole exam this way. But it's, of course, it's easy when someone else does it, and it's less so when you have to do it. But does that make sense? So this is going to be sort of a general reactor separator. Now, there could be circumstances where it's a little bit different, but for an exam type question, you know, an overall balance is a really good place to start off with. In more advanced processes, sometimes what you'll have to do is, we'll talk about this later on in the class, is you actually break this stream apart into 2, right? And we'll call this stream 8. And then you copy stream 7 and you paste it into stream 8. And this is a numerical trick that allows you to converge the system. So you're kind of pseudo simulating how the reactor accumulates materials, right? So if you know that your single pass conversion is a certain amount, and you know the quality of your separation here, what you can do is you can feed your reactants. Initially, it's mixing with nothing. It converts. You do the thermodynamic calculations on the phase separation. You determine how much you want to purge, and then you copy and paste and do the whole process. So then eventually everything will accumulate. So that's another strategy that you can do to solve reactor separator problems. For this purposes, you need a computer to do that. So I wouldn't worry about it on the exam. Right? You would either be given what the recycle rate is or what the composition of the recycle is, the single pass conversion or the overall conversion. And usually you'll want to work with the overall conversion because that's going to be dictating the economics of, hey, can I actually make money if I can convert 80% of this into products? So this is so there's a question I got 10 minutes ago. I apologize for not monitoring the chat. This is homework 3, number 7. So it builds on a question from homework 2 as well. Okay, more questions. We have 14 participants. Who is the bravest of the 14 that wants to ask a question?
Could I ask about like a new question that you
Yes,
could
please.
do? So
Yeah,
I
yes,
think, Olivia, so homework 2, question 7, I believe.
2 questions. Okay, so this is another reactor separator question. What you're asking about? Okay, the reaction A to B is a reactor separator. Feed is 100 moles of A. 100% of the product B is removed. 10% is purged. The flow rate of the purge stream is 5 moles per second. Okay.
Yeah. So I don't know the answer, and I would like to know the answer for that one.
Oh, yeah. Sorry, I've had a bad week. I have not posted these. So what I can do is I can just pop them into Canvas right now, the full solutions.
Oh, that'd be great.
So it's going to be a terribly interesting homework session, but it may help alleviate some concerns. But this one, the example that you're asking about is more straightforward than the one we went over. And so we can cover that one pretty nicely. Okay, homework solutions. Just give me 2 seconds here. 2, homework 3.
Can I ask a quick question about like your grading?
Yeah.
So
For the homework grading or for the exam?
the homework grading, because when I did question 7, but I didn't get any points for it. I might have completely done it wrong, but they didn't tell me about any points that I got for it. Does that happen?
So did you have any work performed on it, or you just?
Yeah, I had work on it. It's just they didn't put any number or put any points for it.
Is it possible it was an oversight and they overlooked it?
I don't know. So I was wondering, like, do I send an email and to like who about that?
Yeah, send an email to me and I'll pass it along. So I'm not doing the homework grading. The TAs are doing the homework grading. So I will look into it if you can pass that along to me, because it could just be a simple oversight.
That's what I'm thinking. So thank you so much.
Okay, so the homework solutions, the full ones are in Canvas. I'm going to delete the short ones because they have the same information that's redundant. And then we will go over and solve this problem together. Okay, sorry about that. All right, so the question homework 2, number 7. So let's do a fresh board here. So we have a reactor separator again. Okay, we have 100 moles of A coming into the system, right? Moles per second. This is exam, so we're stressed for time, so we have to truncate some detail. 100% of the product B is recovered in the bottom stream, and 100% A goes to the top. So again, we can just label these 1, 2, 3, 4, 5, 6, 7. So all of the A goes to the top in this separator. So this is NB4, NA6. And it tells us that the flow rate of the purge stream is 5 moles per second. So this is 5 moles per second of A. Our reaction is A goes to B. So in this case, a molecule balance is actually going to be the easiest. So 1A consumed is equal to 1 mole of B formed. So if we were to do a, let's say, a B balance, our balance would be out equals generated. So in minus out plus generation minus consumption equals accumulation, right? There's no accumulation, there's no consumption of B, there's no feed of B, so out equals generation. So if we have, well, we could also do an A balance as well, but basically if we have 5A left, that means we have to have produced 95 B. But if we wanted to show that rigorously, we would want to do an A balance and solve for what's the rate of consumption of A, and then know that 1 consumption of A is 1 formation of B. So if you want, I can go through that detail, but basically NB4 is equal to 95 moles per second. So the question asks us, what is the overall conversion of A? So A conversion is equal to N minus out over N. So in we have 100, out we have 5 divided by 100, and that results in 95% conversion. There, this is a question for me, or are you guys chatting? Okay. Question C is, what is the rate of formation for B for the whole process? So this is the rate of formation of B. We did a molecule balance. We already solved for that one. And then what is the recycle ratio? This is the ratio between moles fed to how much is purged. So we have a design specification here. It says 10% of the top stream is purged. So that means this is 10% here, and this is 90% there. So what I like to do here is 0.1 is equal to N6 over N5, and 0.9 is equal to N7 over N5. Then you can just solve this, set them equal to N5. So N5 is equal to N6 over 0.1. But this is just algebra. And this is a situation where there's many ways to skin a cat. This is just the way that I like to think about it. I mean, maybe it's easiest just to solve for N5. Let's just do that. So N5 is equal to 50. So that means N7 is 45. Therefore, the recycle ratio is 45 over 100, 0.45. And let's double check. I didn't botch this. Yep, 0.45. Okay, so how does everyone feel about reacting balances, extent of reaction, combustion? So we've covered 2 reactor separator examples. What else can I help with? Was everyone good on the practice exam? Should I be an auctioneer, going once, going twice, end of help session? I'm happy to stick around.
4 on the practice exam.
Is there a question you'd like to ask about it? I think I have it here. Let's see.
Yeah, I just, I'm not sure how like intuitively the solution makes sense, because when I did it, I thought something else. And like, I understand why you did what you did.
Which one?
Part C of question 4.
Or C. Okay. Intuitively, so this is just a big old unit conversion problem, basically, right? The combustion balance plus unit conversion. So part C. Okay, so for every carbon, we make 1 CO2. And- okay, so which part do you want to go over here? Because I'm looking at it right now. I'm refreshing my memory on it.
Part C. Have it?
Yeah, let's see, 150,000 kilograms for 16,000 homes, 400,000 households. So we have to use, let's see, where do I? Oh, I asked for the air product. How many megatons? So here. I can go over it, but I wondering if there's a more specific part that you were confused about.
Part C.
Part C, yes. Which part about part C were you confused about? Which step? Yeah, go ahead.
I think it was just kind of like why you use the things you did. I mean, I don't know, it just,
So, okay, so 1.5 megatons a year, that was part B. So, so in this one here, my starting point is I wanted to know how many, I'm gonna call it delta centers. I think it's back to the delta center now. Vivint Smart Home Marino is a stupid name always. Is 400,000 homes. So when I'm setting up this is a big complicated unit conversion. So when I'm setting these ones up, what I'm trying to do is get to the end point on the left-hand side, and then choosing the starting point that is the most starting, right? So I could have said like is equal to 1 Salt Lake County, right? But I did that conversion in my head. 1 Salt Lake County is 400,000 households. So in the problem statement, it says that we are using 1 megawatt power plant is good for 16,000 homes. So that means 16,000 homes is 100 megawatts. Then a coal-fired power plant that is 100 megawatts uses a total of 50,000 kilograms per hour. So I'm more or less just sort of copying down the solutions, but breaking it into the steps. So stop me if which part is not clear. So then homes cancels with homes, megawatts cancels with megawatts. And then the next step is now I have kilograms per hour of coal. So I'm going to get this into cubic meters. So 1,400 kilograms of coal is 1 cubic meter. So now I have cubic meters per hour. I need delta centers per year. So I just need a time conversion, and then I need a volume conversion. So then the next step in my solutions is that 1 delta center is 800,000 cubic meters. That counts as with this. So now I have delta centers per hour, and then I just need to convert this to days. So 1 day, 24 hours. Oh yeah, 1 day is 24 hours because this is in the denominator. That cancels with that. And then lastly, 365 days is 1 year. And then days cancels with days. And the final answer is 9.78. So a whole lot of coal, but it's a whole lot of homes as well. That's 500,000 homes. But it helps visualize just how much the energy needs are for our current society. I don't know if that helped.
No, that was good. I figured out what I was doing wrong. Thank you.
Okay. Yeah, what I find the hardest part in these types of questions, usually the left-hand side is pretty easy because that's what I'm asking you, but sometimes it's easier to break it up into multiple steps. So choosing what the left-hand side is hopefully going to be the more intuitive one. What can be a little bit more difficult is choosing what's the starting point on the right-hand side. So on this particular problem, if you had chosen a different starting point on the right-hand side, you wouldn't have necessarily been able to get to delta centers per year, but you could always assume a basis and then scale that basis up as well, right? So you could figure out how many cubic meters per year does a single household use, and then you could scale that up to 400,000 households. So that's another totally valid way to do this. I just put it into one big chunk of work, but it could be broken up into multiple smaller steps too. Okay, how confident is everyone feeling for tomorrow? I'll give you a couple of pointers for my tests and general engineering test taking. My advice is read the question, and if you don't instantly know how to start it, then skip it. Don't fall into the trap of reading a question and then looking at it and going, oh, I should know how to do this. And then you kick yourself and you're like, I just need to think about it and I will remember how to do this, right? Don't fall into that trap. Save that until the end of the exam. So look at a question, and if you don't immediately know how to solve it, then move on to the next one. But don't convince yourself that if you just stare at it for 5 minutes, it'll all come to you. Because there will be questions on the exam that you will know how to begin right away. Start with those ones, right? Don't run out of time never having looked at question 5 or 6. The point values that I assign to exam questions have 2 considerations. One, how much physical work does it take? If it's an easy problem that requires a lot of calculations, that may be worth more points. If it's a problem that doesn't require a lot of work, but it's maybe a new process you haven't seen before, right? Then I'll make that worth some more points as well. So high value point questions are going to be ones that require a lot of steps or have a little bit of a curveball and some trickery inside of it. So not every 10-point question is necessarily, a 25-point question may not take you 2.5 times as long as a 10-point question. But each one of these questions, if you know the pathway to attack it, should only take you a couple of minutes to solve. So what you really want to do is knock off those easy ones that you know how to solve. You can knock them down in 5-10 minutes. And then at the end, then you can commit to those questions where you may not exactly know the starting point to solve them. But if you take that time at the beginning and then sort of feel bad about yourself because you're like, I should know how to solve this. I should know how to solve this. Then you'll sink costs into trying to solve one problem when there might be a very low-hanging fruit later on down in the exam. So if you don't instantly know, flip, go to the next question. Okay, last minute questions?
Is there any particular lectures that you've given that you would recommend to go back through to fill up our note sheets or anything, or any equations?
I mean, the homework. So if you used an equation in the homework, I would recommend that, for your sheet. The tough part about this part of the class is it's more like system-based. So, there's not that many equations that we've used. Conversion is one that we use, the hydrostatic equations, the manometer equation, common processes, but it's really quite algorithmic. And the actual equation side of things is, once you practice it a couple of times, it sort of becomes intuitive. So I would say for the second exam, you're going to have a lot more equations that you're going to want to write down, a lot more definitions. But yeah, I don't know, maybe just some example problems that you could squeeze into a box, but nothing that immediately comes to mind. Conversion's one we use a lot. Manometer would be nice to be able to cancel some things out, draw a picture of a manometer and cancel some things out, but yeah. Sorry.
Okay, thank you. Helpful. I think I'll do some examples. Thank you.
Yeah. And ultimately, my objective or my hope would be that you spend a lot of time preparing your equation sheet and then you never look at it. And that's not a bad thing. Making the equation sheet is just a way that I can kind of encourage people to do some early studying. Because if you didn't make the equation sheet, you could just open up your laptop or your phone and then just scroll through the solutions and be like, oh yeah, that makes sense. Oh yeah, that makes sense. Oh yeah, that makes sense. But the actual act of writing and reproducing the solutions on your own for any problems that you got wrong, it helps it seep into your brain a little bit better. And they've shown that writing down notes does improve your conceptual recollection. So the act of writing out the equation sheet is an act of studying and improving for the exam. So even if you don't use it, making it will help you do better. All right, well, I'm going to sign off. I'll upload this video to the Canvas playlist. Any last minute questions? All right. Well, thank you all so much. See you tomorrow morning.